Hello from the Forcetronics YouTube channel. Welcome to Tips on Improving ADC Measurement Accuracy and Resolution, and this is going to be part 2 in a 4 or 5 part series. You actually don't have to see part 1 to watch this one. In part 1 we went over some of the basics. In part 2 we're going to get a little more advanced topics, and actually we're going to talk about a SAR ADC, which relates to this picture you're seeing on the front cover. Before we get started, as always, I'll mention check out Forcetronics.com for information on our for-pay design, manufacturing, and training services. If you like what you see here, please hit the thumbs up on the video, and if you're not already a subscriber, please subscribe to my YouTube channel. All right, let's get started. Okay, here's the agenda for the series. I already kind of mentioned that part 1 was a good foundation if you're new to measurement statistics and just understanding some of the measurement uncertainty, accuracy, things like that, and some of the basics of an ADC. Part 1 is right up your alley. I got a great response from that video. In part 2, we're really going to focus on the architecture of a SAR, or Successive Approximation ADC. Understand how it works and some of its limitations. And a SAR ADC is the typical ADC architecture you find in microcontrollers, right? And that's one of the main topics I cover is microcontrollers. So understanding how the SAR ADC in a microcontroller works can help you better utilize that ADC in the microcontroller. You can also find SAR ADCs outside of single chip ADCs, but I'm going to talk to them from the standpoint of a microcontroller mainly. And then in part 3, originally what I'm going to cover in part 3, I wanted to cover in part 2, but I just realized it was too much material. So in part 2, we'll talk about how a SAR ADC works, some of its limitations, how to calculate how long it takes to make a sample. But in part 3, we'll actually demonstrate some of its limitations and how to overcome them. And we'll also talk about how you can sort of oversample with them to get a faster ADC sampling rate if that's what you need, as long as you understand the trade-offs you're giving up when you run it a little faster than what it's spec'd for. All right, in part 3, we'll talk more about software ways to increase measurement accuracy and resolution. And then in part 5, I'll still plan that out. There are a lot of different topics we can cover. But let's dig into part 2. Okay, as I mentioned, most microcontrollers use a SAR ADC. And in fact, one thing a lot of people don't realize is a lot of microcontrollers only have a single ADC inside the microcontroller, but they use a mux or a multiplexer to switch to different pins. So your microcontroller may advertise that most of the pins can be used for an ADC, but they're really going to a single ADC, meaning they can't sample in parallel typically. That's not true for all of them, but for most of them. And this single ADC architecture in most microcontrollers is a successive approximation ADC, or a SAR ADC. And once again, if we know how a SAR ADC works and we understand its limitations, we can increase our measurement accuracy when using it, and even we'll show in some cases speed up its sampling time. Okay, here's a deeper dive into the architecture. So let's first start on the top. So an ADC, a SAR ADC, has sort of 2 stages to a measurement: the sample time and the hold time. And the hold time is where it's actually calculating the output or the digital value of the analog input signal. So let's start at the top picture. Ignore the triangle that's named SAR, and let's just look at the resistor, the R ADC, and the C ADC. So the VIN is our pin where our analog signal's coming in and we want to make a measurement on it. And this first arrow up here is essentially can be thought of as a switch. So when we want to sample, when we're doing the first stage of the measurement, this switch is closed by the ADC or by the microcontroller, and our signal is allowed to enter the ADC circuitry and charge this capacitor. And once this capacitor is charged, our sample time is over. We open the switch, removing the signal that we're measuring from the ADC input, or isolating it. And then the hold time, or the SAR, where it does the calculation of the value, is then done. So we're charging our capacitor up to the voltage of the input. We then remove the input and then calculate the value based off that capacitor. And once again, I'm making assumptions that we're familiar with how capacitors work. I'm going to make assumptions later how op amps and DACs work, that you have a basic understanding of that. So an important thing to note is the amount of time it takes to sample with a SAR ADC is based off of this resistance and capacitance on the input. So the higher the resistance or the higher the capacitor, the longer it's going to take to charge this up because the RC time constant is higher. The smaller it is, the faster it will charge up. But you can obviously probably imagine that when designing these ADCs inside the microcontroller, there's trade-offs if you make the resistance too low or the capacitance too low versus high. But it's important to note that the sampling time is dependent on these two values. It is also dependent on any impedance or resistance on the input signal, but we'll talk about that later. Okay, let's jump down to this picture on the bottom right. So we have our analog in, which is basically our V in on this upper picture, and then we have our track and hold. This represents this input impedance or this resistor and capacitance that is used to sample the signal so we can feed it to the successive approximation ADC or SAR ADC. So that's what this box represents. So now the rest of this is looking in on this upper triangle up here. So how it's done is, and it's actually not that complex, is you have a comparator circuit, and the most simplest way to do a comparator is an op amp. And what happens is a comparator takes an input, two different inputs, a reference signal and an input, and compares them. And basically what you're doing is you're saturating an op amp. Instead of having a feedback that controls the gain of the op amp, you're basically allowing the op amp to drive the saturation. And whether it drives to the negative rail or the positive rail for its output depends on which one of these is higher. So whichever one is higher will drive the output of this op amp. So let's say minus is ground and plus will be whatever the reference voltage is or the max ADC input value. That's what will come out of this comparator. We'll think of those as ones and zeros. So a saturated op amp to the high power rail or the positive power rail represents a 1. And driving it to the negative power rail represents a 0. And that's actually how we create our 10-bit, 8-bit, or 12-bit string of binary values by the output of the comparator. The other thing that's used and that's important is a DAC, a digital to analog converter that's built into the ADC. So it's based off of the reference voltage. Remember, we talked about that in part 1, how important it is to have an accurate reference voltage. And then the DAC, using this reference voltage, divides it down to smaller values to slowly close in. You can almost think of it as divide and conquer to what this V in value is that we're getting from our charge capacitor. And you could imagine, since we have to do this comparison multiple times, this has a very high input impedance because we don't want to drain the signal from our capacitor that's charged up. And remember, when this is happening, the analog signal is isolated. So we put our DAC value, if you can imagine the first bit or the most significant bit, we put our DAC value to half of Vref. We compare it. If Vin is above half the range of the ADC, this returns a 1. If it's below, it returns a 0, and it tells the DAC or the circuitry what value to use next. And we can kind of see this on the chart to the left. If we think of this as a 4-bit ADC, we do half of Vref, right? The Vin is our input signal that's coming from our charge capacitor. We see here that half of Vref, our signal is less than, so our most significant bit will return a 0. This comparator, because VDAC is higher than Vin, will slam to the negative rail and basically create a 0. Now our next value, which is 1/4 of vref, you can kind of see how they would divide it down, is going to be less than the input signal, so it returns a 1, right? Because Vin is higher than Vdac, so the comparator slams to the positive rail, and that's our output, a 1. So for our next one, it's going to be a 0 because Vin is less than Vref. And then, of course, for our least significant bit, it's going to be a 1. And you can see we don't ever get to the exact value of it. We're just closing in on it. Now, if we had 12 bits, we would be very close to it. So we talked about the track or hold sample time, right, to charge up the cap. And then we just talked about this process, stages of this successive approximation happening from the most significant bit to the least significant bit. Now, each of these takes time. Typically, the successive approximation aspect of it is longer than the track and hold. The track and hold is pretty short. But you can see the more bits you want from this type of architecture, the longer it takes to make the measurement. Right? So we saw some trade-offs on speed. Right? There's a trade-off on how fast you sample versus how many bits you want. Okay, with that in mind, let's look at determining how long you need to sample to get an accurate representation or an exact representation of the signal you're sampling in this charged capacitor. Right, so there's some math here involved, but let's go through this and we'll see why understanding this is important. Because they don't really give you this value in the data sheet of the ADC, but we can sort of play with the ADC a bit and understand its limitations if we understand how to do this calculation. So what I decided to do was to show you to get an accurate sample based on the bits you're trying to achieve, how to calculate that time for just the sampling stage. And remember, it's going to be highly dependent on this RC time constant, which, because of the value of R and C, basically determines the time to charge up the cap. And remember, an RC time constant is not at the cap fully charged, it's the time it takes the cap to get to certain points in its charging cycle, and one RC time constant is 63%, and you can see this is a non-linear curve. Once again, I'm assuming you've seen this before or have some background on RC time constant. If not, just look up a tutorial on capacitors. Okay, so for my first example, I'm going to use actual specs from a 10-bit ADC inside a microcontroller, and for the second one, a 12-bit ADC. And to be transparent, I'm using the Atmega 328P because I use a lot of Arduino stuff, which is found in a lot of the older Arduino products. And then for the second ADC, I'm using the SAM D21, which is a much more advanced, higher cost ADC. We can see the bits are different, and we can see their input impedance is different. Not surprisingly, the lower cost and older AD microcontroller has higher capacitance and resistance values. And for the other one, the SAM D21, which can sample faster, even at 12 bits, it has a much lower capacitance and much lower resistance. Now, this makes the design complexity higher, but it delivers a higher value to the end customer typically. Okay, so to calculate the needed sampling time based on the ADC bits, so we need to know how many bits we want to achieve, and we need to know the RC time constant. We can use the following equation. Now, I get this equation from a application note or a white paper, but once again, if you haven't done math in a while, this means ln means natural log. So this is the natural log of 2 to the power of the bits. So for one case, it's 10 or 12 to the denominator of the least significant bit fraction. So that's a little confusing. But what we want to do is to make sure that our measurement is going to be accurate even out to the least significant bit, we're going to want to make sure we settle to 1/4 of the least significant bit. Now, if you want, you could do 1/2, or you could do 1/8, or you could do 1/16 if you wanted. But this is a common 1/4 is a common way to use it to ensure you're getting good accuracy. Or charging it up for a good representation of the signal. Now this equation, natural log to 2 to the power of the number of bits to the denominator of the least significant bit fraction, comes from a derivation. Now I'm not going to go through the derivation. I just copied it out of this application note and put it in here. I will provide a link in the video description to this application note in case you want to see how they derive this. But this is basically creating a multiplication factor of the RC time constant to determine how long we need to sample our signal to get a good accurate representation of it in this capacitor, charged up in this capacitor. So for the first ADC RC time constant, once again, to get to 63% of charging the cap, we need 448 nanoseconds. And I got that by using this simple formula of capacitance times resistance. So this is the first ADC, this is the second ADC. Oh, and I actually see a mistake here. This should be 3.5. I'll correct that in post. But anyway, this comes out to 12.2 nanoseconds. This, not surprisingly, this one is much lower than this one, right? More expensive microcontroller, more modern microcontroller. So you would expect it to have a better ADC. Now, for the first ADC, to settle within 1/4 of the least significant bit, we do natural log of 1024, and that's 2 to the 10, because it's a 10-bit ADC, times 4, right? Because we're doing to the 1/4 least significant bit. We get 8.23. Now for the second ADC, we have a higher value here, because we're going to 2 to the 12, because it's a 12-bit ADC. We have 4096 times 4. This number is the same, and not surprisingly, we get a higher number, 9.7. So to get a good accurate reading, we need to let this charge up to 9.7 RC time constants, because we have 12 bits, where this one, we only need to do 8.3 because we're using 10 bits. We could let it charge longer, but it doesn't really get us anything because we're limited by the 10 bits. So if we multiply our RC time constant by the number of time constants it needs to charge up to get a good accurate reading, we get 3.73 microseconds for the first ADC, and we get 118.3 nanoseconds for the second ADC. Once again, orders of magnitude lower than the first one, but not surprising because it is a more advanced one. Now remember, this time is not the whole time it takes to make our measurement. It's just the time we need to sample. Remember, sampling and then doing the SAR calculation are the two main timing aspects of how long it takes for your ADC to make a measurement. Now, if we look at the data sheet, the first ADC takes 13 clock cycles total for a measurement at its fastest pace, at its fastest pace. They say 1.5 of these 13 clock cycles is the sample time, and 11.5 is the hold time, which is not surprising, right? The hold time takes a lot longer because we have to do out to the number of bits we want to do. Now, this could be faster if we're not doing a ton of bits. Some ADCs have settings on the number of bits you want to calculate, which will change this time, or I should say the overall time of the ADC measurement. For the SAM-D21, the sample time is a full, for this microcontroller, it's really synchronous to whatever the clock is for the ADC. And remember, when I say clock cycles, I should point this out, I'm talking about ADC clock cycles, and you can set the clock for the ADC, right? This is not the system clock. So the sample time is a full clock cycle, which is a little misleading. It's really actually a half a clock cycle, and then there's a gain calculation they do, or an optional gain calculation they do. But we'll just say for intensive purposes that the sample time is a full clock cycle, and its calculation or hold time is only a half a clock cycle per bit. So basically, they don't give a spec for it, they basically just tell you. And the idea here is, so that means if we were doing 12 bits, it would be 6 clock cycles, and the sample time is 1, so that's 7 clock cycles. The SAM-D21, once again, is more advanced. You can actually set it for 8-bit or 10-bit, which reduces the amount of clock cycles so you can do a faster measurement. Okay, so let's calculate the overall minimum sample rate for each microcontroller to achieve the resolution based on the specs and the value of its RC time constant. Once again, this is not necessarily the spec time. In fact, I show you what the spec time is for the maximum sample. This is what we're going to calculate. So, minimum clock rate we need, we can get it by doing the time it takes to make a sample and divide it by 1.5, because that's what they say the sample time is in clock. So, and then we times it by 13 to get the total time. So the total time for the Atmega 328P to make a measurement that's 10 bits is 32.33 microseconds. If we assume that there's no other delays in making a measurement in free run mode, its max sample rate is 30.9 kilosamples per second. Now, what the max sample rate they spec is only 15 kilosamples per second, so it's much slower, or twice as slow as this, and we'll explain why they do that in a second. For the second ADC, it's all based on clock rates, which makes it a little easier. So our sample time for the second ADC, our sample and hold time is all based on clock cycles. So if we assume that we need 118 nanoseconds per clock cycle, because that's the time it takes to do a sample, and a sample is one full clock cycle, we times that by 7 because we want 12 bits, and each successive approximation calculation per bit is a half clock cycle. We get 828 nanoseconds. That equates to a maximum sample rate, assuming there's no other aspects that delay one measurement from another, which there could be, is over 1 megasample per second. But they only rate it for 350 kilosamples per second at 12 bits. Okay, well, why do they put these lower than what we just calculated as the possible maximum sample time? Well, there's non-ideal aspects in there that they could be including. There also could be some kind of delay from one measurement to another, but often in free run mode there's not. There also could be limitations on how fast the successive approximation can work. But there's also a big factor, and I'll point that out. There's another factor besides all those other ones I mentioned. But it's the input impedance, or how weak or strong the analog signal is you're measuring. So I think one of the easiest examples is, let's say you're using a voltage divider. Let's say you're measuring a 10-volt signal and you want to divide it down. Well, typically we're going to divide it down by tens of kilo ohms or more, or we'll use, I should say, 10 kilo ohm or 20 kilo ohm or whatever resistors to do our dividing. Well, guess what? That adds to the input impedance of the whole measurement. So we calculated the time it takes to charge this capacitor. Well, if I stick another huge resistor out here, I just added to this value and I just affected the time constant of the sample time. So, for instance, in the Atmega 328P data sheet, they say if your signal has 10 kilo ohms or less, you can run it at this maximum sample rate and not have to worry about anything. But if it has more, then they're not guaranteeing the specs at the max sample rate, and they're basically saying you need to lengthen the sample rate. They don't really tell you how, but they tell you need to lengthen it. And understanding these equations and how to do this calculation can help you do that. Now, this is another reason why they're not going to spec it for the absolute fastest rate because they're assuming that you're using at least 10k ohm output impedance. Now remember, when an analog signal has some type of impedance or input impedance, or the signal itself has an impedance, if it has a voltage divider, that's very easy to understand. But a weak signal, such as a thermocouple signal or a piezoelectric signal, has some type of impedance that could be high. Even though you may not have a resistor there, it has some impedance. And what that means is it can only source so much current. This is typically what it means. It can only source so much current. So if you have a huge capacitor and a lot of resistance, when that ADC goes to sample, there's not going to be enough current to charge up the capacitor to enough time constants to get an accurate representation in there, and that's going to cause you accuracy problems. Right? I hope that makes sense. Also, another thing to note is, let's say we don't necessarily need our signal to be super accurate. Well, then we can reduce our measurement time or sample at a faster clock rate with the understanding that we can make faster measurements, but we're losing some accuracy and possibly some resolution. But we can run SAR ADCs at faster clock rates than they're spec'd for, and microcontroller manufacturers allow you to do this. They just don't provide you specs. They leave it up to you to determine what you're giving up. And understanding how we did some of these calculations can allow you to see how fast you can run the ADC. And in fact, those two topics are going to be what we talk about in part 3. So now that we understand how the SAR ADC works, let's talk about making sure we're making accurate measurements with signals that have high impedance, and how to overcome that, and making actually their impedance very low. And then we'll also talk about pushing the sample rate higher and some of the trade-offs you're doing. And actually in part 3, we'll show some real example measurements. I know that's always funner when you see some real life examples. So that's what we'll do in part 3. Okay, that's it for part 2, where we went over the architecture as a SAR ADC and how to calculate and understand the time it takes to sample. If you have anything to add, please use the comment section, or if you have any questions that are specific to this video, please use the comment section. Thank you for watching, and I'll see you back for part 3.